This is a continuing lecture that is part of a set of lectures and notes having to do with continuous time, linear time invariant systems. And in this set of notes, we have been looking at representing LTI systems as differential equations, representing them according to their impulse response, representing them in their frequency domain by their transfer function and their frequency response, h of j omega, and finally a state variable representation, which we have not yet talked about. So last lecture introduced the idea of the impulse, the Dirac delta function, and representing an input u of t to a system as a infinite weighted sum of impulses, and from that we were able to derive a corresponding output that ultimately was expressed in terms of the impulse response h of t and the input u through the convolution operator. And so I want to continue with that now. We want to look at some properties of the convolution. So let's go back. Oh, I guess I have it right here on this page. So we'll start right here on page 21 of the notes. And here we have an LTI system. The input is u of t, the output response is y of t, and we are evaluating the output, or computing the output, through the convolution integral. Now, if we consider different types of systems, primarily causal versus non-causal, then we can change and restrict the limits of our convolution integral from being plus and minus infinity to something that's finite. So first, if the system is non-causal, that is h of t is non-causal, and u of t signal is non-causal, then we have to evaluate the integral over all of time. And the way you can think of this is that if u of t is defined for negative time, and h of t is also defined for negative time, then we have to evaluate the integral over plus and minus infinite time. If both the systems are causal, meaning that here u of t is equal to 0 for t less than 0, and h of t is equal to 0 for t less than 0, then we can limit the limits of integration to 0 and t. So let's take a look at that. If u of t is 0 for negative time, then that is going to put a limit on the lower bound, right? There's no point. We're integrating over tau. And negative values of tau would produce u of t, u of tau, that'd be 0. And then similarly, for our upper limit, if tau goes beyond our variable t, then h, the argument of h, becomes negative. And again, because h is causal, it is 0 for negative time. So this leads to the upper limit being time. And so that helps in evaluating the convolution integral. So you can look at the other permutations, but I want to move on to a couple other properties, I guess, of the convolution integral. We previously mentioned that the derivative of the unit step 1 of t, so that's unit step, was equal to the impulse function, or we could write the integral of the impulse function from negative infinity to time is equal to the unit step. And because we're studying LTI systems, if you operate on if you have an input u, produces an output y, if you operate then with a linear operator on the input u, the output will then become just a version of y in which y has been operated on by that same linear operator. So for instance, if you take the integral of u, then the output will be the integral of y. So we can put that to use here in determining the unit step response given the impulse response. So the unit step response we're calling g of t, just like h of t is the impulse response. And so because the unit step is the integral of the impulse, we then can calculate the unit step response as being the integral of the impulse response. So this is handy. This is a handy result here. It's easy to get the unit step response given the impulse response. And the unit step response is one of those responses that is often desired when we're studying LTI systems. This was mentioned before, but some properties of convolution. Convolution is a commutative and associative, so we can write these two statements here. All right, so associative and commutative. And this third one is interesting, is that the convolution of A with B is equal to the convolution of the nth derivative of A with the nth integral of B. Okay, so we could say then this is equal to A dot convolved with the integral of B. And that would be the same thing as the convolution of A with B. So now let's look at an application of some of these properties. So we're given a unit step. Forgive me for the multiple notation here. 1 of t is the unit step going into the system, and that produces an output g of t. So assume that we are given the step response. We're not given the impulse response, just the step response. And we're asked to find the response of the system to an input u. Now we know that the response of the system is going to be the convolution of u with h, but we don't have the impulse response, but we do have the unit step response. Unit step response is the integral of the impulse response, and so we can take the derivative of the input u, convolve it with the unit step response, and that's what we have here. So knowing g of t, the unit step response, we can find y of t for an arbitrary u of t without first finding h of t. Rather, we just convolve the derivative of u of t with the unit step response. Okay, now we want to look at actually how do we find the impulse response h of t of a system if we are given the differential equation description of the system. So what we're looking to solve is the system where, or the differential equation described by linear operator L operating on the impulse response and being driven by an input delta t. All right, and for all time greater than 0, the right side is equal to 0. Okay, so the first thing we observe is that the impulse response is going to have the same form as the homogeneous solution. Okay, it will have the functional form of the homogeneous solution. So it's that should be comforting. The homogeneous solution is pretty easy to find. You just find the characteristic equation, find the roots, and then you have a number of e to the st terms, either real values or you might have complex conjugate pairs that make up sinusoidal or decaying sinusoidal terms. All right. So what we simply need to do is solve for the coefficients in our impulse response solution form. Okay, so most of the work involved in, at least in this derivation right now, of finding the impulse response from the LDE is simply involved how do we determine those initial conditions. So the rest of this presentation is going to deal with that. The notes provide a more detailed derivation. I don't know if I'm going to go through that. I might. If I do, I'll switch over to a blank sheet and kind of write it out. But let's start by considering, as an example, the first order system, and then we'll generalize after that. So in a first order system, we're going to have a linear operator L that's simply going to be a coefficient times first derivative of y plus 1. So what we're the LDE that we're looking at solving is this one right here. And in order to find the initial conditions, we're going to integrate the LDE between 0 minus and 0 plus. The reason that we're going to do that is recall that the delta function is, we can't really work with the delta function directly because it's 0 valued for all time that's non-zero, and at time 0 it's undefined. So instead, if we integrate both sides, then on the right side, when we integrate the delta function from 0 minus to 0 plus, we'll get the area under the impulse function, which will be 1. So when we're solving for the impulse response, we're always going to have the right side be equal to 1. That is the right side of an LD that's been integrated from 0 minus to 0 plus. So what happens on the right side? Well, we're going to integrate a1 times the derivative of h, so a1 h dot, which simply turns into a1 times the integral of dh, okay, dh from h0 minus to h0 plus. And h0 plus could be non-zero, but we know that h0 minus is going to be 0 because we're going to assume that we have a causal system. Okay, a causal system. So this leads to a1 h0 plus being equal to 1 over a1. Okay? Or if we put it more loosely, we can drop the h0 plus and we'll just say h0, the initial condition on h, is 1 over a1. And what is a1? a1 is just the coefficient in front of the first derivative. Now, let's look at a second order system. And rather than using these notes here, let me jump to another a blank sheet here. Okay, and perhaps I can drive this more clearly and more directly. So let's say that we have an a2 d squared plus a1 d plus a plus 1 operating on h of t equal to the impulse. And so what we're going to do is we are going to integrate both sides. Now in this case what we're going to do is we'll integrate both sides, and then we're going to come back and do the same thing again, but we're going to double integrate both sides. Okay, so we'll have a, and here when we're taking the integral of I'll go ahead and write this one more time. Integral, all of these are from 0 minus to 0 plus, okay? I'll leave that off, but it's all from 0 minus to 0 plus. So we're going to integrate h double dot, okay, h double dot plus a1 integral of h dot, dt, plus integral of h is going to be equal to 1. Okay. Now this first term can be rewritten, since it's really d dt of h dot. Right? So what we really have is the integral of dh dot. And we're going from h dot 0 minus to h dot 0 plus. That'll be plus a1, and here we'll have the integral of dh from h 0 minus to h 0 plus. And then this will be this is going to be the integral of h. Okay, well this will be plus 0, right? Because if you integrate over an infinitesimally small period of time, that will evaluate to 0. Okay, so we'll have a2 h dot 0 plus minus h dot 0 minus plus a1 h 0 plus minus h 0 minus is equal to 1. Now h of 0 minus is 0. Nothing's happening with h for negative time. Same thing for the derivative of h. So we can write a2 h dot 0 plus plus a1 h of 0 plus is equal to 1. Okay, but that's not enough because we have two unknowns here, right? So we're going to have to do a little more work. So if we double integrate our system, so here, let me just rewrite it directly. We're going to double integrate. So we'll have, I'll rewrite this out, a2 double integrate h double dot dt plus a1 double integrate h dot dt plus double integrate h dt, and that's going to be equal to the double integral of the impulse function. On the right side, when we double integrate, we will actually get 0. Alright, so we're going to be integrating 1 for an infinitesimally small period of time, so that integrates to 0. Over on the left, we'll have a2, and let's write this in 2 steps. We'll do the integral of d dt of let's rewrite that here. Okay, double integral of d dt of h dot dt, right, which can be rewritten as the integral of, or the double integral, which can be written as the integral of h dot dt, right, which can be rewritten as d dt of h dt, right, and this will cross out, and so we'll have a2 integral of dh from h 0 minus to h 0 plus. And by now we know that h 0 minus is 0, so we'll write just a2 h 0 plus. Okay? Then let's look at the next term. We'll have a1 double integral of d dt of h dt. This will cross out, and we will rewrite this as the integral of h dt. And because we're integrating over an infinitesimally small period of time, there's no area under that curve h, and so this is going to evaluate to 0, and this whole thing is going to be equal to 0. So what does that leave us? It leaves us with a2h0 plus 0 is equal to 0, which means that h0 plus is equal to 0. And so now we can take that back over here, and we can claim, therefore, h dot 0 plus is going to be equal to 1 over a2. Okay, and h of 0 plus is going to be equal to 0. Okay, so we can, let's summarize here what we know so far. For a first order system, the initial condition is going to be h of 0 plus, or loosely put, h of 0 is going to be equal to 1 over a1. For a second order system, h dot 0 plus is equal to 1 over a2, and h of 0 plus, I'm going to leave the pluses off now, I guess I'll leave them on it, that's more strictly correct, is 0. For a third order, we can show that h double dot of 0 plus is equal to 1 over a3, and the other derivatives of h are equal to 0. Okay, and so you can go on and on and on. So let's, for instance, in a third order, you'd have an a3 y triple dot plus a2 y double dot plus a1 y dot plus 1 is equal to sigma of t, delta t, I'm sorry. And so we're using this highest power coefficient. So we would say h double dot is going to be 1 over a3, and h dot and h are going to be equal to 0 at t equals t plus. So we can look at an example. Let me switch back over to the notes, and we'll just look at an example here. So here's the example. We have a system defined by the linear operator as follows. It has its third order, okay, third order, but it's already been factored for us. The auxiliary equation, or characteristic equation, is right here. It has roots of -2, and then complex conjugate roots of -2 plus and minus j4. And so this is just like finding the homogeneous solution. So we're going to find a solution form for the impulse response that will be the same form as the homogeneous response. C1 e to the minus 2t plus a sine and a cosine term, C2 e to the minus 2t sine 4t, and C3 e to the minus 2t cosine 4t. The initial conditions are going to be, since this is second order, we will have the second derivative, I'm sorry, because it's third order. Because it's third order, we will have the second derivative of h at time 0 equal to 1 over a3. And a3 in this case is the highest power let's see, the highest power in our linear operator, which is d times d squared, and it's 1 d cubed. Okay, so that's why we have a that's why this is equal to 1. If we had a yeah, so that's why that's 1. The first derivative and the 0th derivative are both equal to 0. Okay, so we have 3 unknowns, and we now have 3 equations. H is equal to 0, H dot is equal to 0, and H double dot is equal to 1. And now you just have to do the work. So first, H0 equal to 0. Leads to C1 plus C3 being equal to 0, so we have a constraint that C3 is equal to minus C1. Take the derivative of H and set that equal to 0, and that leads to ultimately to C2 being equal to 0. Okay, and then take the double derivative of H and set it equal to 1, and that leads to 4c1 minus 12c3 is equal to 1. And we know the relationship between c1 and c3, so just plug that in, and we can solve for c1 and for c3. And we have our impulse response, which is a decaying exponential minus a decaying sinusoidal exponential. And this is what it looks like. Then we can check the result. I checked it in MATLAB, and here we see the solid line is the computed MATLAB computed impulse response, and the blue line is the exact solution that we computed. Okay, lastly, what we want to talk about is, I think it's, no, not before lastly. Before lastly, we want to talk about how to find the impulse response for a system that is of the form L operating on Y equal to LD operating on U. So the new element here is, what if the right side is not purely U? What if it's a weighted sum of derivatives operating on U? So to do this, we're going to define a modified system initially. So the original system here is just U of t yielding Y of t. And we're going to define a modified system H hat of S producing Y hat. And we'll find the impulse response for Y hat, or for H hat, and then come back and calculate the impulse response for H of S from that. And here's how we do that. So we're going to define Y hat relative to Y as follows. Okay, and so it's a little different way of defining it. You might think it should be Y hat is equal to something related to Y, and here we've actually written it the other way. But let's just try it out and see what we get. If we take Y and we plug Y into our system, okay, so and then substitute our LD operating on Y hat, then what we get is we can commute LD and L, which leads to having LD operate on both sides, and we can satisfy this modified differential equation by basically satisfying the simpler differential equation. L operating on Y hat is equal to U. And now you see why we defined Y hat as we did here, because it ultimately allows us to have a simplified system involving Y hat, where the right side now has no driving operator LD. So find the impulse response. What we do is we find the impulse response H hat of t, and then we can find the impulse response h of t of the original system by simply evaluating the LD operating on h hat. So let's do an example here. So we're asked to find the impulse response h of t of the following system: 2d plus 3 operating on y is equal to d minus 5 operating on u. So we define a modified system. We define a modified system, 2d plus 3 operating on y hat equal to u, where y hat and y are related here. Okay. To find y hat, we find the roots of L, which are just minus 3/2. So y hat of t is c1 e to the minus 3/2 t, and the initial condition is going to be h at time 0 is equal to 1 over a1, which is 1/2. So h hat of t is 1/2 e to the minus 3/2 t. And then to find h of t, all we have to do is operate on y hat, or h hat of t, with d minus 5, which is done right here. And we find the impulse response of the original system. Okay, lastly, we want to finish up the convolution topic by relating our impulse response of the system to the frequency response hj omega. So we're going to begin with the definition of our convolution here, y of t being equal to the convolution of u of t, the input, with h of t. We are going to consider the special case where u of t is actually a sinusoidal excitation, e to the j omega t. We'll put that in our convolution integral, and we're going to separate this exponential here into the time-dependent portion, e to the minus j omega t, right here, and e to the minus j omega tau, which we will leave inside the integral. Now, we're going to return to what we had discovered about LTI systems previously, and that was that if you have an LTI system and you excite it with an e to the j omega t or e to the st, the response of that system is also going to be e to the j omega t, but scaled by some generally complex scalar lambda. And we also found that that scalar happens to be the frequency response of the system if we're exciting it with e to the j omega t. And so now let's take a look at what we have right here. We have y being equal to something here weighting e to the j omega t. That something is precisely the frequency response, h of j omega. So we can say that the frequency response can be found from the impulse response by evaluating the integral h of tau e to the minus j omega tau over all time. And now this is somewhat tedious to do. I mean, you can we typically don't do this, at least for complicated systems, but it is a correct relationship here. And what's interesting, and you might have some insight in this if you have studied some Fourier transform before, but look at this integral. This integral is actually the Fourier transform of the impulse response. So we'll look at Fourier transform later, but if you've studied Fourier transform before, you'll recognize that as simply being the Fourier transform of our impulse response. That is the frequency response. So here's a simple example to finish up, and it is simple. It makes the frequency response derivation from the impulse response look simple, but it's only because it's a simple system. So it's first order system, an RC circuit, and our impulse response is going to be just an exponential decay. Okay, so we put that in here, and we multiply it by e to the minus j omega tau, and then we integrate from 0 to infinity, not minus infinity, because of the unit step here on our h of t, it's causal. And we see that we arrive at what we know to be the case for a simple first order system. It's going to be 1 or scalar over a 1 plus j omega term.